Section 1.2, chemical concentrations. So this is something you definitely want to get very, very comfortable with because we are going to be doing this throughout the entire course. So this is straight review, and no worries if you're rusty, but we're going to do this over and over again until we are not rusty anymore. So first, we need to be able to know the definition of these things because a lot of the definitions of these concentrations will change. And sometimes they'll use solution or solvent or solute. So you need to be able to understand the difference between them. A solution is a mixture or dissolved mixture of two or more substances. A solute is a minor species in solution. A solvent is the major species in solution. A good example of this is if I wanted to make some tea, I would take tea leaves and I would dunk them into some boiling water. And the tea would represent my solute. That's what I'm dissolving into another substance. So the boiling water will be pulling out, the caffeine, the goodness out of those tea leaves. So the water, solvent. The solution is the combination of tea plus water. Most examples in this course concern aqueous solution. So we kind of always assume that our solvent is water unless we say otherwise. You also need to be able to be comfortable knowing what a mole is. A mole is an amount of substance. So technically, if I was to say, okay, I have this many atoms, that is 6.02 times 10 to the 23rd atoms equals 1 mole. But you're not always going to be asked to go between atoms and moles. Sometimes you need to use the molecular weight. So molecular weight is grams per mole. So if I go to the periodic table of elements, that's going to be, I have this much weight per 1 mole. So it really just depends on the question. Don't assume that just because I mentioned moles that you have to know Avogadro's number or use it. So atomic mass is the molecular weight. It's from the periodic table of elements. That's grams per mole. Molecular mass is the sum of atomic masses of atoms in a molecule. Element. And then this is for like a compound. So like CO2, that's going to be the molecular mass. If it's an individual element like gold, that's an atomic mass. Formula mass is just molecular masses of strong electrolytes, but typically these kind of go synonymously. You can use them back and forth. It gets you the same answer in the end. Let's talk about concentrations. Concentrations have a bunch of different things that fall under this giant umbrella, but some things you see a lot more often than others, but you need to be comfortable knowing what they are. So it's a quantity per volume or mass. So how much solute is contained in a given volume, and that volume could be solvent or it could be solution. So it's very important to know the difference depending on the definition. What we use the most in this class is molarity, so capital M. And whenever you see a capital M, you'll notice that I will take out the capital M and replace it with moles per liter. But that liter on the bottom is not just liters of solvent, it's liters of solution. So it's moles of solute divided by liters of solution. So that would be solvent plus solute. For molality, or lowercase m, I will also replace it with its definition, but this is very different on the bottom. So the top is still the same, moles, I cannot spell, solute, divided by kilograms of solvent. We typically will use this when we're dealing with weights that are mixtures, like solids that are mixtures, and then if it's liquids, you use capital M for molarity. So you need to be very comfortable knowing the differences between them and how to go between them. Electrolytes are going to be ionic compounds. So remember, ionic compounds are going to be a mixture of a metal plus non-metal or strong acids and bases. That would be under strong electrolytes. If it's a weak electrolyte, it's going to be weak acids and bases. So I'm going to take out the strong and just replace it with acids and bases because acids and bases typically won't be metals, but they are still under the umbrella of electrolytes. So strong electrolytes will 100% dissociate, so it turns into the ion. So if I have NaCl, which is a strong electrolyte, and I dissolve it in water, so it starts off as a salt, and if I dissolve it in water, that will turn into Na plus Cl minus. So it breaks up into its ions 100%. So if I were to look at this, there is no more NaCl combined, it's all Na plus and Cl minus. Whereas a weak electrolyte will partially dissociate, so some of it will turn into its ions, but most of it will remain as its, starting compound. Formal concentration is the molarity of a substance if it were not converted into the species in solution. So that's the total number of moles in solution regardless of any reactions that take place. So just going to be normal concentration. Okay. Let's practice. Typical seawater contains 2.7 grams of salt, so NaCl, per 100 milliliters of seawater. What is the molarity of NaCl? So with these, it's sometimes hard to get started, but I typically will think about what is my given and what is my goal or my want. My want is molarity. Molarity is going to be moles of NaCl, that's our solute, divided by liters of solution. So that's our goal, but we're starting with 2.7 grams of NaCl. Do this unit and this unit match? No, they don't match. So the first thing I would have to do is convert grams into moles using the molecular weight. So I would go to the periodic table of elements, I would go find sodium, I'd go find chloride, I'd add them up and get the molecular weight, which when I do, it is, I think it's 58.435. So NaCl, 58.435 grams per mole. So to use dimensional analysis, I would like to put moles on top and grams on the bottom. So that's grams per 1 mole. So I'll put a 1 here and 58.435 grams on the bottom. And that gives me 0.0462 moles of NaCl. So I have my top number. Now let's figure out the bottom number. They give us a volume here. They give us 100 milliliters, but I can't just plug that in because down over here it's in liters. That's the same thing as you writing 100 times 10 to the minus 3. So they were nice enough to give that to us. If you ever needed to convert that, you would just do 100 times 1 liter divided by 1,000 milliliters. That's the same thing as 0.1. But since they gave us 100, I'm going to plug that in. So if I have 0.0462 moles of NaCl and I divide it by 100 times 10 to the minus 3 liters, I get 0.462 molar NaCl. So you can leave it in moles per liter or you can convert it back to M, capital M. Number B, or letter B, says magnesium chloride has a concentration of 0.054 molar in the ocean. How many grams of magnesium chloride are present in 25 milliliters of seawater? So it looks like we're going backwards on this one. We're starting with concentration and we're trying to get rid of some part of it to be left with grams. So it's literally the same problem, but in reverse. You'll see that what I do is typically when I see a capital M, I do not leave it in the problem because if I can't see the units that are in there, I can't make conversions to help answer. So I will always write the moles of solute, in this case it's magnesium chloride, divided by liters of solution. This tells me, or shows me at least, I can do something here. First, if I'm trying to get rid of or do something to go from moles per liters into grams, I can't have anything in the bottom. I just can't. It has to be just one thing and it's on the top. So I have to come up with a way to get rid of the liters of solution on the bottom. So the only way you can do that is by multiplying it by liters. That way, liters divided by liters is the same thing as 1, and those units are canceled. So I need to multiply it by a volume. They do give us a volume, but they give us a volume in milliliters. So I can do a quick conversion, 25 milliliters times 1 liter divided by 1,000 milliliters, or I can just move the decimal place over 3 times. Okay. Now my units can cancel, and I'm left with just moles. I'm going to move that down here. Okay, so this one's going to be a little bit simpler because now I'm going from moles to grams. In order to do that, I need the molecular weight of magnesium chloride. So I go to my periodic table of elements, I find magnesium, and then I have chloride again. I multiply the chloride by 2, and the molecular weight of magnesium chloride is going to be 95.196 grams per mole. So to get rid of the moles on the top, I want to divide by the moles. So 95.196 grams. That way the moles cancel, and my overall answer will be 0.12885, so that might round up, so I'll just do 0.129 grams of magnesium chloride. If the problem is giving it to you in 2 sig figs, I could even round up one more time, so that would be 1.3 grams of magnesium chloride. So that's a great way of thinking about how to do the overall answer. But notice how I didn't round earlier. I didn't round the molecular weight. I rounded at the very, very end. A says, this one says molarity of salts in the sea, but A says calculate the formula mass of calcium sulfate. So I would just need to go to the periodic table of elements. Calcium is 40.078. Sulfur is 32.059, and then oxygen, and there are 4, is going to be 16. So 15.999 will round up to 16. So I have to just add all of these together, and the formula mass is 136.137 grams per mole. And I'm not going to round this one because you want to keep all those decimal places. B says, what is the molarity of CaSO4 in a solution containing 1.2 grams of calcium sulfate in a volume of 50 milliliters? So this is very similar to the previous problem where I need to go from grams to moles, and then I need to go from milliliters to liters and then divide them into each other. So, but I'm going to go a different route for this one. I'm going to kind of combine everything in one to save a little bit of time. So instead of us dividing it all at the very, very end, I can kind of put them together. 1.2 grams of CaSO4 per 50 milliliters. So this is another way you can answer the problem, but pick what works best for you. So if you don't like this way, don't do it. Do it the previous method. If I would like to go from grams to moles, I'm going to change out and put moles on top and then grams on the bottom. That way those grams are going to cancel. This is where you put the formula mass from the previous problem. Okay. Now I have my top number for molarity. I just need to figure out the bottom number. So I'll do a different color. I have 50 milliliters on the bottom, but I want it to be liters on the bottom. So there are 1,000 milliliters per liter. Now my milliliters will cancel, and my overall units are going to be moles per liter. So we are good to go. We can type this into the calculator either by multiplying everything on the top by everything on the bottom, or going one at a time. All right, so when I plug everything in, I get 0.176 molarity CaSO4. C says how many grams of CaSO4 and 50 milliliters of 0.086 molar CaSO4. So this is just the same exact question, but we're going backwards. I'm starting with 0.086 molar. Instead of me doing capital M, I'm going to replace it with moles of CaSO4 per liters of solution. So I want to go from moles per liters to then, let me do arrow instead, to just moles and then just grams. So to do that, I have to get rid of the liters on the bottom. So I have to multiply it by liters on the top. So I need to convert 50 milliliters into liters by dividing it by 1,000, or just moving the decimal place over 3 times. Okay, now my liters are gone and I'm left with moles. To go from moles to grams, we need to multiply it by the molecular weight. And now the moles cancel. So our answer is going to be in just grams. Not too bad. Just make sure that you get comfortable. If you want to practice these problems over and over again, you can always just replace numbers and then practice the same math. But the setups are never going to change when it comes to questions I could ask. All I would do is be throwing different compounds at you, different volumes, but it's very straightforward, and the more you practice it, the better it gets. Another way that we could say concentration would be using percentages. So you might see weight percent or volume percent, and sometimes they'll have like weight per volume percent, but those are also under the umbrella of concentration. The definitions are going to be very important for these. So for weight percent, that's going to be a mass of solute divided by the total mass of the mixture times 100. So like if I was to say this is 10 weight percent, that's the same thing as me writing 10 grams of solute divided by 100 grams of solution, because remember 10% is going to be 10 per 100, or you can do it like 0.1 grams of solute per 1 gram of solution, as long as when you divide them into each other, they equal 10. You could also just like divide by 100, and then that's it to get rid of that percentage. If it's a volume percent, that's the same thing as weight, but you're now replacing it with volume per volume, but the percentage are the same. So make sure that you are comfortable being able to convert a percentage into what its definition is. Let's practice converting weight percent into molarity and molality. This one says find the molality, and we'll do, this says find molarity, and then we'll do molality on the next slide, of 37% weight of HCl. So that WT is for weight, meaning it's grams for grams. And then the density of substance is the mass per unit volume. The table, okay, so they'll give us a table on this page after the periodic table on the front. Tells us that the density of HCl is 1.19. So they gave us a lot of information. First, let's figure out how we're going to get there. If they give us a weight percent, instead of me leaving it in that percentages, I am going to convert it into its definition. So remember on the previous slide, you can either do 37 per 100, because when you divide them into each other, it needs to equal 37, or 0.37 per 1. So it's solute per solution. And it's saying find the molarity, which is moles of HCl per liters of solution. So on the top, we're going to have to go from grams to moles using molecular weight. And then on the bottom, we're going to have to go from grams to milliliters using density. And then go from milliliters to liters. So we can do several different things here. First, you can break this up or leave it together. So if you're more comfortable kind of like just seeing this 37 here and converting it to grams, to moles, that's one way you can do it. And then, or you prefer to leave it all together, it's really up to you. The molecular weight of HCl is 36.454 grams per mole from the periodic table. If I want moles, I have to divide it by grams, 36.454 grams of HCl They cancel, and I'm left with moles. And you don't have to round too soon. Like you want to kind of wait till the very end to round. So I tend to use extra decimal places to make sure I'm very exact. Okay. Next, if I have 100 grams of solution, I would need to use my density to go from grams to milliliters. That's what this number is going to give me. I want to use dimensional analysis, so I'll have milliliters on top and grams on the bottom. And then lastly, I need to have in liters because molarity is moles per liter. Sorry, 1 liter. Okay, so everything should cancel and my answer will be in liters. Okay, the last step is to divide them into each other. 1.04149 divided by 0.084 will give you 12.1 molar. I'm going to show you the way that you could do it if you do it all together, but it's going to give you the same math in the end. So if you prefer to break it up like I have here, then continue. You're going to get the right answer. So I'm going to erase this and I'm going to show you how you can do it all together. So I'll go back to 37 grams of HCl per 100 grams of solution. And I want moles on top, so I'll keep that mole per 36.454 grams. And then I want liters on the bottom. So I want to go from grams to milliliters. Okay. So grams will cancel. So that's what these grams belong to. These grams will cancel. These milliliters will cancel. And the last is going to be moles per liter. So my units make sense. And when I plug this into my calculator, I get 12.1 molar HCl. So you need to decide what you feel best doing. Then it says find the molality. So we need to start back from the beginning. If I have a weight percent, that's 37 grams of HCl per 100 grams of solution. This is when it's very important to understand the definition of molality. Molality is going to be moles of solute, in this case that's HCl, per kilograms of solvent. This is not the same thing as this. So if I was to convert 100 into kilograms by dividing it by 1,000, you would not get the right answer. The way that you want to think about this is you want to think, okay, the definition of solution is solute plus solvent. If in this 100 grams I have 37 grams of solute, how many grams of that is going to be solvent? We'll use the basic math. If 37 plus blank is equal to 100, I just have to take 100 minus 37, and that will get me the grams of just the solvent. So that would end up being 63 grams if I did that math of solvent. So this is the value that needs to be converted into kilograms. So if I take the 63 grams and divide it by 1,000, that will end up being 0.063 kilograms. So it's not so bad. But I think that's the trickiest part of this question, is trying not to let this 100 be converted into kilograms, because that 100 is solution, not solvent. But I was able to easily break it up and figure out specifically just the solvent. Now the top part is going to be the exact same as we did on the previous problem. If I need to go from grams to moles, I just need to use the molecular weight. So 37 grams of HCl and then divide by the molecular weight equals 1.0149 moles. And then if I divide that by my kilograms, ooh, can't write. I can find that the molality is 16.1, and I can use a lowercase m or leave it as moles per kilogram. Not so bad. If you got tricked by this, I highly recommend just taking this number and replacing it with a different number and practicing it a few times until you're more comfortable. Because the nature of this problem is not going to change. All I would be changing is the compound and the percentage, but it's very doable the more you do it. All right, let's do a practice question. This is very similar to what you could see on the ACS final. This says the density of 70% weight ACS reagent grade parts per caloric acid. FM is just formula mass. That's just going to be molecular weight. And the units are going to be grams per mole. The ACS exam tends to give you this value a lot to save you time, but they don't give you the units. So we need to be able to say, okay, FM formula mass is grams per mole from the periodic table of elements, and they give us the density. Calculate the molarity. So this is exactly like the previous question. All they did was change the percentage and they changed the density, but the setup is the exact same. If I see a weight percentage, I'm going to say 70, and that's grams of our solute, HClO4, divided by 100 grams of solution. And it's asking for molarity. So I need to go from grams to moles, and from grams on the bottom to liters using density. So let's set that all up. On the top, I need to go from grams to moles by dividing it by the molecular weight. Okay, so that gives us moles on top, so our top number is good. Now let's get the bottom number. So grams of solution to milliliters of solution, we have to use density. I want milliliters on the bottom, and that is 1.664 grams on top. And then lastly, I want liters on the bottom, so I will do 1 liter, 1,000 milliliters. So all my units should, sorry, wrong one, should cancel. And I should have moles per liter. All right, when I plug this into my calculator, I get 11.6 molar, so which means 3 will be the right answer. This is a great question to practice because it's very similar to what you'll see on the final and potentially my exams. The next part of concentrations is going to be a new concept, and that's going to be parts per million, or ppm, and parts per billion, or ppb. The definition, of course, is going to be mass of a substance divided by mass of sample times 10 to the 6 for ppm, or mass of substance divided by mass of sample times 10 to the 9. But to be honest with you, I prefer these bottom definitions because when I'm doing the math on these, it's just better to have units than to leave it as this. If you feel more comfortable doing that, feel free, but I will be doing my math using these bottom ones. So you want to be very comfortable kind of recognizing 1 ppm is equal to micrograms per milliliter or milligrams per liter. So they're kind of synonymous. And then ppb is nanograms per milliliter or micrograms per liter. So if I were to say, like, I have 10 ppb of something, I would instantly do 10 micrograms per liter, and that would help me greatly with the math. So let's practice. Normal alkanes are hydrocarbons with the formula HCnH2n plus 2. Plants selectively synthesize alkanes with an odd number of carbon atoms. The concentration of C29H60 in summer rainwater collected in Hanover, Germany is 34 ppb. Find the molarity of C29H60. So it looks like we will need the molecular weight of this compound. So just remember each of those carbons, there's 29 of them. If I look at the periodic table of elements, 12.0096 plus 60 hydrogens, 1.00, I think it's 008, is 408.799. So you have the molecular weight. The next is when I see ppb, I want to change it into its units because I just don't like looking at ppb. So 34 ppb is the same thing as me writing 34 micrograms per liter. And this looks so much better when I'm trying to convert something into molarity, which is moles per liter, because all I have to do is now convert milligrams to moles, and I can leave the liters the same. So much easier versus having to do the whole mass per mass times 10 to the 9. It just is not as pretty. If I want to convert micrograms into grams, because, you know, to be able to convert into moles, you need to have grams. How many micrograms are in 1 gram? Micro is very, very small. The equivalence is going to be 1 gram equals 1 times 10 to the 6 micrograms. So I want grams on top, and I want 1 times 10 to the 6 micrograms on the bottom. That way they cancel, and I now have grams. The next thing I have to do is convert grams to moles using the molecular weight. So 1 mole divided by 408.799 grams. The good news here is I do not need to do anything to the bottom because now I have liters in the bottom and I have moles on the top. That's all I need to do is to figure out the molarity. When I plug this into my calculator, I get 8.32 times 10 to the -8th molarity. The reason why we convert things into ppm and ppb is because the molarity, the molality, the percent weights, it's just such a small number that it makes sense to like leave it in ppm or pp to represent that very, very small number. But you can tell 8.32 times 10 to the -8th molar of C29H60. This problem is not going to change. I'm going to give you probably another paragraph and say, okay, find the ppm of this or find the molarity of this. It's very straightforward as long as you know that ppm is milligrams per liter and ppb is micrograms per liter. There's so much doable if you remember that conversion. Let's practice another one. What is the concentration in ppm of copper, so just copper 2+, and they give us the molecular weight of just copper, and a 2.7 times 10 to the -4 molar aqueous copper sulfate. This is definitely going to be an ACS style question. It's good practice, but it's going to be backwards from the previous problem. So if I have 2.7 times 10 to the -4 molar, which is moles of CuSO4 per liter, I'm going to try to get that molar into milligrams. But first, this is not really a necessary step for the math, but it's a step that kind of just proves. I'm just going to focus on the copper. So let's think, if I have 1 mole of CuSO4, how many moles of just copper? Look at the number after the element. If there's no number itself, that you can assume it's a 1. If I was to ask you to think about the oxygen, you can say there's 4 oxygen, but copper is going to be a 1 because there's only 1 copper. So 1 mole of Cu2 plus per 1 mole of CuSO4. That conversion is important. All right, next step. I need to figure out what is the milligrams, but to do that, I have to find grams first. Which one of these am I going to use? Am I going to use copper sulfate, or am I going to use copper by itself? Well, this is that necessary step. I have converted my moles of CuSO4 into just copper. So I have to use 63.546 because it's asking for the concentration of just copper. And then lastly, to convert milligrams into grams, I have 1 gram equals 1,000 milligrams. I'm going to multiply it by 1,000. All right, so my units should cancel, and I should be left with milligrams per liter. Right, so when I do all of that math, I get 17.157 ppm, which leaves answer option 4. Remember, if you were to actually plug in the wrong value here, it will get you the wrong answer and it'll be very, very different. So you want to make sure that your units are making sense. You're reading the question a few times to make sure you're really sure and confident in what it's asking.